All right, take 3. This is section 2.5, the fundamental theorem of algebra. Basically, this is all the different techniques of trying to find our zeros, solutions, roots, x-intercepts, that kind of thing. And so on a calculator portion of the test, don't forget you should always try to look at your calculator first. So let's give that a whirl and look at our calculator and see what happens. In this particular problem, if I go into my calculator and I want to take a look at that, what I'm going to do is I'm going to enter in the equation. And so my equation that I have is x to the third power, and then plus 6x minus 7. And don't forget to have 0 in your second one if you want to use the second trace thing. And what you'll notice in the screen down below is that it looks like it crosses the x-axis in exactly one spot. You can also just do that on your calculator by hitting graph if you want to and see the same thing. And it looks like a 1. So let's go back to our notes and let's just give that a whirl and see if it actually is 1. So as I look at using synthetic division, I put a 1 in the seat and I write down the coefficients 1, 0 for the x squared, 6 for the x, and negative 7 is the constant. And then using the process, I drop the 1 down. 1 times 1 is 1, add them up. 1 times 1 is 1, add them up. 1 times 7 is 7. And then when you add them up, oh look, indeed, the answer is 1. Or in other words, 1 is a solution. Now the cool thing about that is that also means that my leftover is x squared plus x plus 7. Sorry. I said x and I wrote down 7. So plus x plus 7. And this does not factor. But when I try to find the zeros, I could use the quadratic formula. So as I use the quadratic formula to try to do this, I know that my x is going to be the opposite of b, and the coefficient there is a 1, plus or minus the square root of that b squared, so 1 squared minus 4 times a times c, all over, everything over, that is, 2 times a. And when I simplify that just a little bit, that means that I'm going to have x equals negative 1 plus or minus the square root of 1 minus 28, which is negative 27, and that's all over 2. And recently we learned that when we're dealing with negatives in square roots, that's really just saying that we have an imaginary number. So what I'm going to do is I'm just going to rewrite that square root stuff using the imaginary number notation. So I'm going to bring that up to the top up here. And as I rewrite it, I'm going to say that the x, sorry, I don't know why it does that, that the x is equal to the opposite of b plus or minus the square root of 27 under the radical, and I, saying that I have an imaginary number outside the radical, and that's all over 2. And we should always simplify things, and 27 actually happens to have a perfect square inside of it, believe it or not. So that means I have negative 1 plus or minus the square root of 9 times the square root of 3 times I on the outside of the radicals, all over 2. And the reason I chose 9 times 3 is because I know the square root of 9. And so then my answer becomes negative 1 plus or minus 3, which is the square root of 9, times the square root of 3, still under the radical, and the I, which is indicating that I had an imaginary number, or in other words, square root under the radical, all over 2. And what you can see now is that we have 1 real solution and 2 imaginary, or in other words, complex solutions. And the cool thing is that you will always have complex solutions or solutions with i's in them in what they call conjugate pairs. So you'll notice there's a plus and a minus there. So the solutions are 1 and negative 1 plus 3 root 3i all over 2 and negative 1 minus 3 root 3i all over 2. 3 solutions. Why were there 3 solutions? There were 3 solutions because we had an x cubed, which means we have to have 3. In problem number 2, it's very similar to problem number 1 in that we're going to find the zeros. You could use the P over Q technique if you wanted to, the rational root test. to see what's going on. And notice that there are actually only 4 possibilities if you do that. So remembering that the stuff that comes at the end is p, and the stuff in the beginning is q for the coefficients, and there's a 1 in front of the x to the 4. I take all the factors of p, which are 1s and 3s, put them all over the factors of q, which are 1s, and both plus and minus, and so I know that my p's over q's are equal to plus or minus 3s and plus or minus 1s when I divide them. So there are only 4 possible real solutions, and let's just say, just for the fun of it, that I start out with 3. And so I choose a 3 to try as one of the real zeros. Again, I could also look on my calculator if I want to and see and verify if I can use a calculator. But you could try these rational zeros, and since there's only 4 of them, if there's going to be any real zeros, there have to be 0, 2, or 4, just in case there are imaginaries. So you can't really have any of that. So at least one of these is going to work if I have any real solutions whatsoever. So I put the coefficients 1, negative 3. There are no x squareds, 1 for the x and negative 3 for the constant. And then using my technique, I see that I have 1 down below, and then 3 times 1 is 3. That produces a 0 when I add. 3 times 0 is 0. Add them up and I get 0. 3 times 0 is 0. Add them up, I get 1. 3 times 1 is 3. And when I add them up, I get a 0, which means indeed a real 0 was 3. And the cool thing is I can continue this technique right afterwards. Or in other words, what I'm saying is that I could use another number from here to check. And since I see positive ones there, in order to get rid of some of those, I'm going to see if maybe a negative 1 would work. So now I use this technique and see, does this indeed work? So I bring down the 1. Negative 1 times 1 is negative 1. Add. Negative 1 times negative 1 is 1. Add. Negative 1 times 1 is negative 1. Add. And oh, look, it is a 0. Which means now I also know that negative 1 was also a 0 to this function. So I have 2 real zeros. And this stuff that's left over on the bottom is representing x squared minus x plus 1, which means I have a quadratic, and I can use either factoring or the quadratic formula. Factoring does not work, so I'm going to try to use the quadratic formula when I set it equal to 0. And if I do that, what ends up happening is I get x equals the opposite of b plus or minus the square root of the b squared minus 4 times a times c, all of that all over 2 times a. And when I simplify, that means that I have 1 plus or minus the square root of 1 minus 4, which is negative 3, all over 2. And we learned just in the previous problem that that means I just have an I. So my answers are 1 plus or minus the square root of 3 under the radical. I have an I, and it's all over 2. And this again is representing 2 imaginary solutions or complex solutions because they come in conjugate pairs, and we see the plus or minus. For a grand total of 4 solutions, again, because we have x to the 4th, which tells me I have 4 solutions. In number 3, we're going to start backwards. They're going to tell us that we have a 4th degree polynomial, which means that I should have 4 roots. And then they also tell me that I have 0, 1, and I as zeros, which means that x equals 0, x equals 1, and x equal I are solutions. But that's a problem because they said it's a 4th degree, which means I have to have a 4th one. So that means I have to have another imaginary, or in other words, the conjugate pair, which would be x equals the opposite of I, because one has to be positive and one has to be negative. So from there, we know that we can have each of these things as solutions, so then we try to move backwards. And when we're moving backwards, that means that x minus 0 is equal to 0, x minus 1 equals 0, x minus I equals 0, or x plus I equals 0. So we're getting 0 on one side, everything else on the other. And then these things become factors for us. So what that means is that I have really x minus 0 times x minus 1 times x minus I times x plus I. And this will end up being our function when we multiply it all out, let's concentrate on the first thing. Let's concentrate on the first two parentheses here and multiplying those out. When I multiply those two parentheses out, I really can ignore the 0. So I'm going to take the x in the first parentheses and multiply by the things in the second. X times x is x squared. X times minus 1 is minus x. So the highlighted stuff in yellow turns out to be the stuff here in this parentheses. Looking at the second set of parentheses, or in other words, the third and fourth parentheses, if I were to FOIL that out, I would end up with x times x, which is x squared, x times I, which is xi, negative I times x, which is negative ix, and negative I times I, which is negative I squared. And so all the stuff in the third and fourth parentheses becomes all of this stuff. And I happen to notice that the middle terms, even though they look a little bit different, are actually the same but opposites, and they cancel out. So just like 3 times 7 and 7 times 3 both produce 21, xi and ix are the same. One's positive, one's negative. They cancel each other out. So really what I can do is I can rewrite this as x squared minus x in the first parentheses, and the second one as x squared minus I squared. Now that minus I squared, don't forget I squared is negative 1. So the opposite of negative 1 is positive 1. And now all I have left to do really is to FOIL these parentheses out. If I do that and I FOIL these parentheses out, x squared times x squared is x to the fourth, x squared times 1 is positive x squared, negative x times x squared is negative x cubed, and negative x times 1 is negative x. Of course, I'm going to write this in function notation because they asked for a function, and in descending order because that's the way that we're supposed to do it. So I have x to the fourth minus x cubed plus x squared minus x as my final answer. In problem number 4,